Hey, what's the derivative of the sine function?
Cosine.
Nice. Alright, in this video, I want to share with you some more examples of U substitution that are going to be a little bit more complex than the first couple that we've looked at. So, Exhibit A, let us go ahead and try to walk through those steps that I outlined in the last video to try to anti-differentiate this crazy looking function. So step one, we're going to let U equal the innermost function. And when you look at the difference between this and this second one is clearly the function that is inside of another function. It's inside of the cosine function. So we're going to let U equal that. And 99% of the time, this is going to be the way to go. If you've got an inside function, you're going to let that equal U. So if that's U, now we're going to evaluate du right away, which is the derivative of U, and we're going to differentiate x to the power 4 plus 4x to get 4x cubed plus 4. So now let's go ahead and try to rewrite the integral. Instead of with x's, though, this time let's try to just use u's. So what I have up here is the cosine of all this stuff that we let equal u. So we're going to write this as the cosine of u. And now what we need to do is look at the fact, oh, and look at this. I forgot something already. When we find du, I forgot my little dx term. It's easy to forget that. It's easy to forget that guy. So let's see here. Right now, if I were to write du, I would be writing this. And what you'll notice is that this 4x cubed plus 4 is not what I actually want. What I actually want is x cubed plus 1. So the nature of the conversation is one in which we are comparing the actual leftovers with what our new leftovers are telling us. So to put this another way, x cubed plus 1 dx is what I need. That's what I'm trying to come up with, this dx and this x cubed plus 1. But what I actually have is 4x cubed plus 4 dx. So what I need to do is figure out how can I modify what I have to get what I need. And you'll notice that if I multiply all this stuff by 1/4, I'll end up with what I need. So what I'm doing is I am multiplying my du term by 1/4 to get, oopsies, to get what I actually need. So, instead of just instead of just du, I'm going to write this as 1/4 du. But that looks sloppy, and if we remember our constant rule, any constant we can chuck out front. So what I've actually got now is 1/4 multiplied by the antiderivative of the cosine of u times du. And then this becomes pretty straightforward. This is going to become 1/4 times the sine of u plus c. And my final step is to replace u with what u is actually equal to, which is x to the power 4 plus 4x. And there we have it. Alright, let's try another one. Let's let our function equal t times the square root of t squared plus 1. And we are going to let u equal the innermost function, which is this character right there. T squared plus 1 is all inside of the square root function. And if u is equal to t squared plus 1, then du is equal to 2t dt. So let's go ahead and write our new integral, speaking the language of u. What I know is that t squared plus 1 all is inside of a square root function, so instead of the square root of t squared plus 1, I'm going to write the square root of u. And now the problem is, when I write du, what I'm actually writing is 2t dt. I don't want 2t dt, I want just t dt. So the question is, what do I have to do to this to turn it into what I actually want? And the answer is, I need to multiply it by 1/2. If I multiply all of this stuff by 1/2, then this 2 becomes a 1, which is what I want. So I'm going to plop that constant of a 1/2 out in front right away and proceed. So now this is interesting, because when I raise my the power by 1, I go from 1/2 to 3/2, and then I need to think about how would I just get rid of that coefficient, and the answer is by multiplying by 2/3. 3/2 times 2/3 would cancel each other out, and then I'm left with the 1/2 still out in front. So really what's happening is, if you're able to see that, by just multiplying by 1/3, when I multiply the 3/2 by the 1/3, I would be left with the 1/2 that I need to be left with. Oh boy. Good, so final step here is to replace u with what u is equal to, which is t squared plus 1 and we're good. So let me show you one more now, which is going to be even a little bit more complex. But again, we're going to follow the same rules and begin by letting u equal the innermost function, which is 5x plus 1, and then du is going to equal 5 dx. And now we run into some new trouble. If I try integrating the square root of u, when I write du, the trouble is I'm writing 5 times dx, and there's two problems with this. One of them is that I'm missing out on this x. I'm not generating an x, and the other problem is that I'm getting an extra 5. So let's focus on the first problem and try to deal with this extra factor of x. So to figure out what x is equal to in terms of u, we can step back to this equation that we've set up, u is equal to 5x plus 1, and we can solve this thing for x. And by solving this for x, we will be creating a statement that is speaking this new language of u. So let's go ahead and just rewrite this equation and try to isolate x. Subtract 1 and divide by 5. Or just multiply by 1/5. So I've got 1/5 times u minus 1, and this is what x is. So good. Let's go back to this integral that I'm trying to set up and see if I can reconfigure this in order to incorporate this x value. And first things first, I suppose, I didn't yet deal with this extra 5. Now we should go back and tackle problem 2 as well. I can deal with this extra 5 by multiplying my du term by 1/5, right? Because 5 times 1/5 will cancel out, leaving me just with the dx. So I'm going to plop that 1/5 out in front of the integral. And now what I'm going to do is deal with this need for this x by multiplying the square root of u by all this stuff, which is 1/5 times u minus 1 du. Now at this point you might be like, what the heck, this is not any simpler than what we started with. And I would actually disagree. This is going to be end up being simpler because I can turn this into a power function, which we'll see in just a minute, which I could not do with this original function speaking the x language. So let's just see if we can algebraically modify this thing a little bit to get this into a simpler term by writing this as u to the power of 1/2, and then I've got 1/5 u minus 1, And let's see what we can do with this. I can distribute my 1/5. And actually, I'm going to go ahead and distribute. I'll just kind of skip a baby step here and distribute all of 1/5 times u to the 1/2 through to this u minus 1 term. So I've got u to the 1/2 times 1/5 times u to the power of 1, which is going to give me 1/5 times u to the power of 1 plus 1/2, which is 3/2, minus, this is a 1, so I've got u to the power of 1/2 times 1/5 times -1. So just u to the power of 1/2 times 1/5. And you know what? This was really silly of me. I should have just taken this constant of 1/5 and chucked it out front with the other 1/5. So let's do that now just to simplify things slightly. If I pull that 1/5 out, I'm going to have a coefficient of 1/25 times the integral of u to the power of 3/2 minus u to the power of 1/2 du. And now I have something that is pretty easy to anti-differentiate because I've just got some power functions. So let's rewrite this on the next page. So here we go. I've got 1/25 out front, and I'm going to raise this by a power of 1 by adding 2/2 to get u to the power of 5/2, and then I need a coefficient of 2/5 to cancel that out so that I can get my invisible 1. And I'm going to play the same game with this next chunk. I'm going to add 2/2 to 1/2 to get u to the power of 3/2, and I need a 2/3 out front. And I'm going to add c to all of this. And my final step here is to replace u with what we originally let u equal to, which was 5x plus 1. And there we have it. A really nasty answer. If I wanted to, which I totally do, I can distribute my 1/25 through and come up with this beautiful final answer.